ಈಗೆಲ್ಲ ಬೆಂಗಳೂರಲ್ಲಿ ಬರೀ ಕನ್ನಡಿಗ ಅಂತಾರೆ. ಸೊ ಏನ್ ಮಾಡೋಣ.
I think you may start, Ramesh ಅವರು. ಇನ್ನೊಂದು ಸ್ವಲ್ಪ
ಬಿಜಾಪುರ್ನವರು. Sure.
Sir, you can start now, sir.
Okay. Good afternoon, everybody. Today we have with us distinguished scientist Professor Anil Prabhakar. He is a faculty at IIT Madras. He will be delivering a talk on translating quantum technologies, our national quantum mission. Before going for his talk, let me give a brief overview of his academic achievements. Professor Anil Prabhakar received his PhD in 1997 from Carnegie Mellon University with a dissertation on the nonlinear spin wave optical interactions. He has been with the faculty at the Department of Electrical Engineering, IIT Madras, since 2002, and he is engaged across multiple laboratories that work on quantum technologies, fiber laser, and optofluidics. He is a member of the Scientific Management Board for LIGO India to detect gravity waves and India-based Neutrino Observatory. He currently serves on editorial boards of many reputed journals, including Scientific Reports by Nature, IEEE Transactions on Magnetics, Journal of Magnetism and Magnetic Materials, and other boards that he is chairing or is being a member, or is the chair of BI's panel on quantum computing. He is also a nominee, Indian representative at IU PAP C9 panel on magnetism from 2021 till 2027. He is also a member PKS Science, Technology and Innovation Committee on Research. He is also a member Joint Technical Advisory Group of the Empower Technology Group, Office of PSA, Government of India, India Scientific Management member, and he is also a member of UGC Expert Committee to frame guidelines for equitable access to quality education by socio-economically disadvantaged group, and he is also a member of the Senate IIIT Delhi. His current research interests in the area of quantum technologies have applications in metrology, quantum communication, quantum computing. As a co-founder of Q New Labs and of Q Fluence, both incubated by IIT Madras, he focused on quantum communication and photonic quantum computing respectively. And earlier startup Unilumen Photonics that focused on fiber laser was acquired by Jiva Sciences. He is currently the director of Yali Mobility and Enability Foundation, companies that focus on rehabilitation engineering. Dr. Anil has published more than 50 research papers in national and international journals of repute, and he has co-authored a book titled Spin Waves, a few book chapters, and he has also obtained 18 patents in a wide range of devices in areas of photonics, magnonics, and assistive devices. With this very brief introduction of vast academic achievements of Dr. Anil Prabhakar, I request Dr. Anil to take over and deliver his talk on translating quantum technologies or National Quantum Mission. I take this opportunity also to welcome Dr. Usha Madam, Dr. Sudha Madam, Dr. Girija and other senior faculties, and all the students who have joined. I'm sure you'll have a lot of take-home message from Dr. Anil sir's talk. I request all of you to ask questions. Don't go with doubts in your mind. This is over to you, Professor, for your talk.
Thank you very much. And that was a very long introduction. I hope I can do justice to all of that. I think over the period of 25, 30 years, you just collect all these things.
Yes, sir.
But let me start, without wasting too much time. So I title these talks usually for the general audience. I call it Translating Quantum Technology. A lot of this work is done with the support of the Emphasis F1 Foundation through our Center for Quantum Information, Communication, and Computing, that we also call as CQUIC, right? Uh, the center itself is very loose, and I'll explain to you how that works. So the background of the talk is that we are all at this National Quantum Mission, and we want to understand what is it about and what is the quantum technology buzz about. I give you some details, maybe not too many, but I want you to leave you with the takeaway messages. How do you translate quantum science into technology? When will you first see quantum technology working at scale? As I said, the focus is on translation, and even the National Quantum Mission has been talking about translation. It is not the same as learning a lot of quantum mechanics, because that is what we call quantum 1.0, where we are understanding the quantum mechanics and the quantum behavior of particles and devices. Quantum 2.0, which is what all the nations are dealing with today, is talking about something slightly different than traditional the understanding of quantum mechanics to make devices better. Right? You heard a lot about my background, but I'll shine it up again very briefly. It is interesting that in 2000 and before 2002, I was working for a company called Quantum. I did not know that I would come back 20 years later, or actually 25 years later, and start working again in quantum technology. But it's not a new thing. The primary difference is previously when we were working on quantum, we were not doing quantum 2.0, we were doing quantum 1.0, where we were working on magnetic tunnel junctions, devices that had the ability to provide sensory capabilities because of tunnel effects, for example, right? But that is not what we are talking about today. We're talking about today something very different, and that's what quantum 2.0 is about. So if you look at our own quantum trajectory, right, my own personal work on what is called frequency coded quantum key distribution began about 14 years ago in 2010, right? We had our first demonstrations of FCQKD in 2010. And my second PhD student who did his PhD on this, right? But it wasn't as interesting then at that time until the quantum computing hardware, which is the second bullet, comes in. And that is when more and more people started looking at it more closely, right? Today, we have a third horizontal where we are building our own photonic quantum computing machines, our own photonic Ising machines. And I'll try to explain to you the difference between these things in the time that I have available. Quantum today, the center is very interdisciplinary. It's not just physicists, there are electrical engineers, there are biotechnologists, there are chemists, metallurgists, mechanical engineers, and even colleagues from management studies who is in our center. We ourselves have been member of an IBM quantum network since October 22, trying to understand a little more about how quantum computing happens. My own experiences are most in quantum networks, but during the pandemic, when I couldn't do any experiments, I picked up quantum computing, and that's where I started understanding a little more of what people are talking about. This is a sort of. Go ahead.
Slideshow full screen for me.
Okay. I like to see my slides, but
okay.
I don't know what's coming up otherwise.
Yes.
What happens out here is that companies like IBM, they start explaining to us that they can create value. And if you see their charts, they're saying that by about 2022, which was 2 years ago, there's going to be an increase in the use of quantum computers. They would hit 400 qubits and then go to 1,000 qubits, and thereafter the future is ours, right? But what exactly are they talking about? And I'm going to blow this up a little bit, or actually it's written at the side out here, right? You have applications, quantum chemistry, optimization, cryptography, and then you have some basic science things out here. So who are the people who are actually going to use this? It becomes a question that one has to answer when we talk about translation. So I'm going to blow it up out here so we can see this a little bit. You'll see out here, there are financial services, drug discovery, materials design. These are very specific industries that we think will benefit. And in the early days, materials design will benefit, and then drug discovery will benefit, and then financial services. And this is important to understand, because if you're not a chemist, not a material scientist, or not a biotechnologist, and you're only doing financial services or optimization type things, you're still further along in the journey. It's not immediate. You may be looking at another 3 to 5 years. Right? The computing race itself, if you look at it, and I've color coded this as best as I can, there are the ones in green who are following what is called superconducting qubits. The ones in light red that are following ion traps. In fact, just yesterday or day before, Microsoft announced, along with Quantinuum, that they have been able to solve a chemistry problem with fault-tolerant qubits. Right? And when one reads these popular articles, one has to understand what they're talking about. There are two companies that do photons, Xanadu and PsiQuantum, and now there's Confluence in Bangalore who are doing photons for computing. If you look at Alibaba, IQM, and Amazon, they also had superconducting qubits, but I think today Amazon may not be pursuing it as aggressively. Intel is pursuing spin qubits, which is a different technology. At the bottom right, I have this line that says circuits versus annealers, and that is also something for us to understand, because not everybody is talking the same language when they talk about quantum computing. You know, IBM will say that they are got so many qubits, then IonQ or Quantinuum will say they have many more qubits. D-Wave will come and say they have even more qubits, and then you're wondering why, if you have so many qubits, why nothing is getting solved, right? And it turns out that the Quantinuum is talking of ion traps, IBM will be talking of superconducting qubits, D-Wave will be talking about annealers. So one has to really start carefully understanding what these things are. Right? If you look at the qubit realizations themselves, and this is what we call gate circuit based, not the annealers. The gate circuit based have different varieties. And in these different varieties, they all have different criteria. Number of qubits, what is the lifetime of a qubit, what is the fidelity of a qubit, what is gate operation time, how long does it take for an operation to happen. So we are also comfortable with classical computing that we can say, okay, you know, it takes the clock speed on my processor is, I don't know, 2 gigahertz. I have a 2 gigahertz processor, multi-core, so I can do a 1+1 operation in fractions of a second, right? Less than a microsecond. Here, each gate is taking a microsecond. Then you are really worrying about how you can actually do simple things with it, right? So one has to understand a little bit before one jumps into all the hype, right? There's a lot of hard work and a lot of interesting physics. So I hope that we will talk about that, right? So today we are in this era called noisy intermediate scale quantum devices, or NISQ devices. And these pictures that you see are not really of a quantum processing unit or a QPU, but they're actually of a dilution refrigerator. The refrigerator takes you down from room temperature at the top all the way down to a temperature of 20 or 4 millikelvin down at the bottom, where you have what is called a superconducting Josephson junction. And these are some old images. Google has been with 72 qubits, IBM with 400 qubits, Rigetti with about 80 qubits, right? And then, as I said, D-Wave will say they have 5,000 qubits, but they are not even doing the same things that IBM and Rigetti are doing, and Google are doing. And quantinuum is, say, they have 150 qubits, but they are iron traps. They are not really superconducting qubits. So it's like everyone's comparing apples and oranges and saying they have the best fruit, right? And you have to decide what fruit you want to really eat. The Chinese, on the other hand, are in a completely different path. They're saying they've got photonic quantum supremacy, right? And they have a path to a scalable quantum computer. Now, this little photograph on the right looks like a very complicated optical table. Imagine getting all these little things lined up, all these mirrors and lasers and everything lined up accurately to build a grid like the one that is on the left, right? It's extremely complicated to build something like this to scale on optical table. And so, people are trying to do photonic quantum computing on chips, right? And that is something that there is a lot of expertise in India, and we are trying to pursue that angle. So let's take a step back, right? And ask ourselves, what is the National Quantum Mission? Right? And here I've put down two of the verticals of the National Quantum Mission. One of them is quantum computing, and the other one is quantum communications. These are the two verticals that I work in. There are two more, one in quantum sensing and one on quantum materials and devices. The quantum computing itself, there is cloud-based hardware, like from IBM, for example, or you can now get access to Quantinuum through Microsoft Quantum Azure. Then there is the photonics version of it. And in communications, there are two pieces that I've marked out. One is called system as a networks, and one is materials and devices. And both of them are equally important to be able to do quantum communications. But it's important to understand this difference between computing and communications. One is the Ethernet. How does my video call get set up? The other one is my computer. Is it a desktop? Is it a Mac? Is it a Linux? Is it an iPad? Right? Computing and communications are two very different things. And in the early days of these conversations, people were getting confused between them. And I like to draw the example to a shield and a sword. The computing is a sword, it's a spear, it's a weapon of offense. Communications is a weapon of defense. In case my enemies have a spear, can I defend myself? That's what quantum communications is about, right? So it's important to understand a little bit of this, right? So we'll talk a little bit about the details, what are artificial atoms, what is a gate circuit model, what is annealing, right? Before I do that, let us understand a little bit of why quantum computing is of interest. So if you have n qubits, right, you can imagine that they form ripples on the surface of a pond, right? So you throw two stones and you have these ripples, and you throw many stones, you have many more ripples. So computational space that n qubits can work with scales as 2 to the power n. So with 8 qubits, I'm already at 256 computational paths. 64 qubits has already become such a large number that I cannot do anything, calculate it and put it out very easily. But if this was the case, why are we not able to do anything right now? It's because we do not have these actual paths. We are saying that in an ideal case, if I have n logical qubits, then I can have 2 to the power n computational paths. But I do not have 16 logical qubits today. I may have 1 logical qubit or 10 logical qubits, right? Actually, maybe not even be 10. So the problem out here is, can we get enough logical qubits which are error corrected and error free to actually leverage off this massive computational path that happens in some sort of a wave phenomena? Just the way waves interfere, we want to be able to use that idea out here, right? If you look at a two-slit experiment, you will understand this little better, that waves interfere in a classical sense. They will all just land up. If you throw tennis balls through two doors, they will all accumulate behind the two doors. But if you have slits and you have quantum particles out there, you will get interference patterns. So what is shown on the right is an interference pattern where you have multiple maxima and minima. And this actually behavior is what we are trying to leverage of when we say we are going to do quantum computation. This is one of the behaviors. There are two behaviors. One is entanglement and one is superposition. This is mostly around superposition, right? And this is the magic of superposition, right? That if I can simultaneously evaluate a function f of x for many different values of x, then I can do the computation only once. So instead of, if I have n different types of values, I don't have to do the computation n times, is what I would do on a classical computer. I can just do it on a quantum computer by doing it once, assuming that the quantum computer does not have noise, right? It turns out that the quantum computer is noisy, and so instead of doing it once, you have to do many times, what we call a shot. And the output is always in a superposition state until we make a measurement, at which point we collapse into either f of 0 or f of 1, right? So this is what we call a projective measurement. So the idea is that it's a superposition state, and instead of just doing a 0 bit or a 1 bit, I have access to all the values, fractional values between 0 and 1. Coming back to this idea of circuit-based systems and annealers, you understand that circuit-based systems are trying to use entanglement and superposition, whereas annealers are just trying to minimize energy. And they mostly work with superposition. There could be some entanglement and tunneling also there, but a lot of it is done with superposition, which is interesting because they use wave-based computing, and that is where photonics also works very well. You can use wave-based computing and superposition with photonics. You can use it with acoustics, anything that you're comfortable with. You do not have entanglement, but if you can solve a problem without it, then why not do that, right? Let me give you some examples of what is happening today. You'll see most people talk about hybrid classical quantum methods. And there are 4 different types. You can do a classical device with classical data. You can do a classical device with quantum data. You can do a quantum device with classical data, and you can do a quantum device with quantum data. So you'll understand that even when people talk about hybrid, it's not the same thing. One has to really peel out the layers and understand what people are talking about, right? So this is a typical example where this is your quantum circuit in brown, and you're doing some adjustment to this blue circuit, which is actually classical, right? And you're using machine learning out there to improve your quantum computer. You're using classical machine learning. So somebody told me, about a couple of months ago, saying this quantum computer is not really a computer. It is more like a very fancy instrument, right? Like an X-ray tomography or something like that, or a MRI machine or something. It's like a very fancy thing. And right now it's not really a computer, which is probably a good description today, right? Now, so why are people interested in this? It's because there are some algorithms, right, that can be solved deterministically on a classical computer in polynomial time. Those are called P algorithms. The NP algorithms, the solution can be checked on a classical computer in polynomial time, right? But what we are interested in solving is a quantum computer in polynomial time, which is a BQP type algorithm, right? And there are some of them. There is Shor's algorithm, there is Grover's algorithm, right? Some of these can actually work a little better on a quantum computer than on a classical computer, right? One has to be careful, but when do you use a quantum computer and when do you use a classical computer, right? If you look at this, you will see that you're actually saying that a search on a quantum computer has a speed up of square root of n over search on a classical computer. What does that mean? It means that as my database size, if I'm doing a Google search or I'm doing a directory search, as my database scales with size n, the amount of time I take on a classical computer scales as order of n, which is this blue line. On the other hand, if you are able to do it on a quantum computer, I'm able to reduce the time it takes. So that's this red line, red curve, right? Order of square root of n. Now here's a problem. If my database size is very small, I can do it on a classical computer. It's faster. The blue line is lower than the red line. It has to go to a large enough size before the red line benefits over the blue line. But if the size of the problem, and according to this graph, is 300 plus, right, where the crossover happens, that means I need 300 plus logical qubits before I can run Grover's search to any advantage on a quantum computer. And today we do not have 300 logical qubits, right? So we are still at this era today where we may have maybe, let's say, 10 logical qubits. Then you're still looking at Grover's search running much slower on the quantum computer than the classical computer, right? So one has to understand what this complexity and these scalings mean. The second algorithm is called Shor's factoring algorithm. And that actually is the real crux of the matter. Shor's factoring algorithm came out in 1984. And in 84, he showed that if you had a quantum computer, you can crack a password faster on a quantum computer than on a classical computer, right? Today's passwords, in a very loose example, is based on being able to factor a large integer into its primes. So, for example, if I say it's 121, then that's 11 into 11, right? Which is very hard to do. Or if I say 143, it's 11 into 13. I can do that mentally because I know my tables up to that point. But imagine it's a very large integer, you can't really find the primes, right? However, I can verify it very easily. If I know that it is 11 and 143, I know that the other person has 13. On the other side, if the person has 13 and he knows that the product is 143, he can divide 143 by 13 and say that the party A has 11, right? So that is the crux of the reason why people got interested, right? Cracking passwords. And that is the holy grail out here. This breaking encryption. And that's still, 15 years away. So now the question is, what are we doing in this interim? And in this interim, we are trying to find these windows of opportunity on what is called optimization, combinatorial logistics, quantum machine learning, where we are thinking that we may be get to the 100 and 1000 qubit level, where we will be able to find some commercial quantum applications, right? And then we may be able to do drug design, data mining, logistics, right? So translation out here also means understanding this opportunity that is available to us and seeing if there is some way to use it. But talking of passwords, the question is whether I really need a quantum computer to crack your password. Today, AI is saying that, wait a minute, you don't even need a quantum computer. Look at this chart. It's like one of the most scary charts that I've seen. It came out last year, right? It says that if your password has 11 numbers, it is cracked instantly using AI. If it has 11 lowercase letters, it'll take 32 minutes. If it has upper and lowercase letters, it takes a month. If it has numbers, upper and lowercase letters, it takes 10 months. If it is 11. If it is less than 11, in 6 numbers, upper and lowercase letters, instantly crack it. And now, if you are looking at numbers and upper and lowercase letters and symbols, and you have 11 characters, then it'll take 3 years. But that is AI in 2023. I'm sure AI in 2024, this table has already changed. And of course, this is assuming that I'm not using some easy passwords to guess, like my mother's name and things like that, right? So AI itself becomes so powerful that it makes you wonder that whether or not we really need to wait for a quantum computer to crack our passwords, right? So what is the alternative? The alternative is to start working on this area of cryptography. So this was the chart, another version of this chart that I was talking to you about, that you have basic science at the bottom level, you have translational research in the middle, and then you have these high-end applications like breaking passwords, drug discovery, new materials, right? So a lot of the work today gets done on these NP-hard problems that are called bin packing and route optimization, right? But there are some of us who are also interested in this cryptography piece of it. So I'll introduce a little bit of that and I'll show you how we do some of this, right? You'll see out here, this is how basic cryptography is done. And you'll see that you're saying that you have two parties, Alice and Bob, and they have a public key and a secret key that is used to encrypt and a decrypt. So in this case, it could be this idea of 11 and 13 and so on, right? There is an eavesdropper in the middle who's always trying to steal information. And your idea is you have some plain text, you have an encryption key, you transfer ciphertext, you have a decryption key, and then you want to go back to plain text. And you want to be able to do this in a reasonable manner, right? Now, why is it important? Why is this cryptography important at all? Because when you are sending this data from Alice to Bob, there's an eavesdropper who can steal the data today. Although the quantum computer is not going to come for another 10 years, they can harvest now and decrypt later. So they steal the data and keep it today, and 10 years later, they will start decrypting it. And 10 years later, they will have all your strategic information. It could be anything, right? It could be the design plans for a nuclear reactor. You don't want that falling into the wrong hands. So that is the reason why we are worrying about this problem today. Here in Chennai, we have built what is called a metro area quantum access network. This metro area network has got, in this picture, it has a node at IIT Madras. It has 2 nodes at the IIT Madras Research Park and 2 nodes at the Society for Electronic Transaction Security. This is an old picture because now it has actually gone forward and it is connected to the National Informatics Center about 15 kilometers away. Right? So we have our first networks of that utilize quantum properties of light. What are the quantum properties of light? It's basically saying that, look, if you remember my double slit experiment, it is saying that a single particle will fall on one of those areas behind the screen. It won't fall in all the areas, but when I measure it, I will be able to say which property the particle had. So using these properties, we are trying to build these networks called the quantum access networks. Right? And if you look at the terrestrial quantum communications, the National Quantum Mission has put a goal for us. It says the intercity quantum key distribution over 2,000 kilometers with trusted nodes using wavelength division, multiplexing, and existing optical fiber. So, a very clear deliverable that we need to do. Why does it use the word trusted nodes? It's because we do not have what is called a quantum repeater today. If I make a measurement, the properties, the quantum properties that are sitting on the photon are destroyed. And a photon could have a very simple idea is it can have polarization. It could be vertically polarized or horizontally polarized. And that becomes a 1 bit or a 0 bit, right? But the minute I make a measurement, I lose that information. So I cannot really build a repeater, a quantum repeater today. And if it is repeaterless, I have a particular limitation that I have up to about 280 kilometers before the rate falls very low, right? And more practically, it's usually about 100 kilometers, not even 200 kilometers. By about 100 kilometers, this rate is minus 20 decibels, which means I lose 1 in 100 photons. So until we have a repeater, we use this idea of a trusted node, which converts from electrical to optical, or sorry, from optical to electrical and back to optical, or an OEO node, right? And this is how our networks will be set up, right? There will be some cryptographic application on the top. There'll be some network devices. You're taking a key from the QKD layer that is down there, quantum key distribution layer, and you're sending the encrypted data or the ciphertext into the user network. And at the other end, the key has also reached, and you're now using it to decrypt. So having done this in the city, we now have plans to do this between Chennai and Bangalore, which is very nice because I'm in Chennai and you are all in Bangalore. So, we're going to connect these two cities, and we call this Kila. So if you look at this one is called Makan, Metro Area Quantum Access Network, which means house in Hindi, for those of you who are not familiar. And this one is called Kila, which is quantum internet with local access. And Kila means a fort, right? And if you look at this slide, you'll see that we are trying very hard to go over the existing fiber that is available to us from BSNL. And we need about 14 secure nodes and 2 metro area networks at the two ends, Chennai and Bangalore, right? And we're trying hard to put everything onto photonic integrated circuits and reduce what we call the swap C, which is the size, weight, power, and cost associated with doing this. Right? And what happens after we do this? We go to the quantum internet with local access, which is we connect Delhi to Bangalore, right? And that is even more challenging. You can imagine connecting a backbone with quantum communications that allows you to take what is there, a user who's sitting in Indore, and connect them to a user sitting in Bangalore or in Chennai, right? So, and along the way, we'll be building these metro area networks in all these different cities, right? So it's a huge endeavor. And the goal is not to actually stop there. The goal is to actually say that, wait a minute, we can do even better. We can build networks that include satellites. So there is, the National Quantum Mission has ideas of putting up satellites that will send photons from base stations out here to different base stations and exchange these secret keys. And then these secret keys will also be available through a terrestrial fiber optic network and uses different protocols. I'm keeping this at a very superficial level, but there are many protocols that people use. This one, BB84, BB84 was 1984, and Shor's algorithm, I think, was 1994, not 84. So BB84 was actually proposed in a conference in IISc Bangalore. So that is something that, again, we take pride in, right? So this is one of the aims of the National Quantum Mission, is to build out a quantum network like this, right? So if you look at the National Quantum Mission, we have verticals. We have quantum computing, quantum communication, quantum sensing, quantum materials. And we are also looking at different technologies, photonics, ion traps. Not so much on NMR computing, because that is ensembles. These are not individual qubits. But there is work on superconducting qubits and spin qubits, right? These are all large collaborations. These are not things that individual people can do. There is significant amount of work that is required, and so we do them with large collaborations. Right? I will skip down a little bit and show you some other pictures that I have. You'll see out here some of the hardware that is built, right? So this is actually just an evaluation board, and the real board that we build is actually fairly small. And then you'll see out here the user interface that connects these networks and decides which nodes have secure keys, right? And which nodes do not have secure keys, right? And how do you secure these things is actually very simple. You secure them in this is one way of securing them, right? So IIT Delhi has got a project that is going to try to build this out on a network. You start off with a source that has entangled photons, right? And entangled photons means that you can have two photons, one, let's say, vertically polarized, and one which is horizontally polarized. And then you send them to the two parties, Alice and Bob. And because if Alice measures the vertically polarized, she knows that Bob has horizontal, or vice versa. If Alice gets horizontal, then she knows Bob has vertical. And so in doing so, they have exchanged a key, right? It's a very simple way of doing things. And then once you have the key, you sort of are transferring information between Alice and Bob. And there is a lot of information theory that goes on at the back end, which is all classical, right? So a lot of translation is actually classical. It is not quantum, right? The quantum parts of it were finished as soon as you had these photons in there, right? So I always like to end talks with this particular slide, which was I pulled out of a Nature paper in 2016. It says, "Unite to build the quantum internet." One of the greatest challenges for implementing a globally distributed quantum computer or a quantum internet is entangling nodes across the network. So you can imagine that if I want to do this particular experiment across my killa, right? I can show it to you in another picture. I just saw it out here. So you look at this, right? This is an experiment that was done by DRDO and IIT Delhi, where they communicated across 100 kilometers of fiber, right? 100 kilometers of fiber is between two places, Prayagraj and Vindhyachal, right? And it's a fairly a complicated experiment because you have to worry about the photon losses down this fiber. And if you remember that rate of minus 20 dB for 100 kilometers, you'll understand that if they send 100 photons out here, at the receiver, they're only getting one photon. So if they want to set up a password of 1,000 bits, they have to send at least 100,000 photons. But usually in a practical case, they have to send at least 1 million or 10 million photons, right? Before they can set up a 1,000-bit key at this end. And this is not done using single photons, it's done using weak coherent states. If you actually do this kind of an experiment, then it's even harder because the entangled source is not very robust, right? It generates entangled photons at a much lower rate than what we call a weak coherent source. So all in all, it's a fairly complicated state of affairs, and which is why we say this, right? Unite to build a quantum internet. So I would encourage everybody in the audience to understand the enormity of the task that is between us, that has been given to us as a responsibility, and say that we are going to do something like this. Let's get together to do it, because it's not possible for any single person or single individual to actually succeed. Right. Let me pause here and take questions.
When are the results of NQM expected, sir?
I don't have an answer to that. I know that we have been going through many rounds of deliberations. There has been shortlisting being done, and institutions have been identified. But I think the deliberations are still ongoing. We do not have official notification as yet on the results of the NQM.
Any other questions?
Hello, Anil. Wonderful exposure to all our audience. As we said, honey, honey, good idre halla. So we have to get together and start doing things. So how would you kind of, we want to plan something in Karnataka that is a training part and creating a quantum workforce at different levels, not mainly only for research, but also a base too, which is quantum work. So do you have any suggestion? That needs a lot of discussion, we know, but
so I mean, I'll give you my disclaimer that I am one of those who is always wary of going down this quantum workforce route, because the industry is not yet ready to absorb large numbers. So students particularly should be aware of that even if you look at AI ML, it did not have any takers for 30 years. And suddenly today, everybody is there. Especially undergrads, I would say they need a broader education and the basic engineering skills that we have. Experimental skills, if you're doing physics, you do experimental physics. I think all of that is invaluable.
Right.
You cannot chase this mirage of quantum too soon, because you will not have a job if you get too specialized too early on. Right? See, today, if I'm building a network, like as the National Quantum Mission has said, build a network. I need people who can do electronics. I need people who can do fiber optics. I need people who are willing to go there and dig in the mud and see where the fault is.
Yes.
It is.
Yes.
as one of my colleagues often tells me, she quotes, I think Perez says, the experiments run in the real world space, not in Hilbert space.
Yeah.
Right. So literally,
Yes.
people who want to get involved have to be willing to do classical things.
Right. Agree.
Now, so again, it's very important to understand communication and computing are very different. So if you're doing quantum computing, you're not really building an experiment today. What you're doing is you're running things on the cloud. And what you're running on the cloud are Python codes. Do you have good Python programming skills?
Yeah.
So I think we have to start there when we start doing this training, because while it is good to have quantum computing on your resume, it's not sufficient is what we are seeing. What we are
Right.
seeing is you need to have all the skills that normally you would get you hired, and then the icing on the cake is the ability to talk quantum computing.
Right.
Right. Even and quantum computing is not universal. Are you doing quantum chemistry? Are you doing
Yeah.
finance?
I agree.
These domain knowledges have become
Right.
extremely important. And I suffer. In fact, if I look at my table, I have a book on finance out here, because people are asking me, "Are you doing quantum finance?" I don't even know finance.
Yeah.
How do I do quantum
Yeah, I
finance?
understand.
Right. So I would be very careful about this quantum workforce. We should not. There is an IEEE paper that I often share. If you read it, they'll say that you really need our engineers on the pyramid, and as you get to the top of the pyramid, you need the PhDs. At the
Correct.
bottom of the pyramid, you need broad skills.
Right.
You
Agreed.
know, simple skills that we have always said
Sure.
are required. So it's not a quantum workforce. I think it's a workforce training that we need to take on, and sort of teach them the language that maybe the PhDs are talking with. But finally, a lot of it is classical work that is happening.
I agree with you perfectly. Thank you for the detailed answer. I have been always saying that we need to have some interdisciplinary kind of syllabus for
Yeah.
this quantum
Yeah.
technology. It is not just physics or not just engineering. It should be combined, and we should have also finance.
Yeah.
So is what I try to say. So, but there are some very small islands where somebody teaches this kind of courses, but it's not yet kind of spread all over. Why I want to say this is it should be at least known. Say, for example, during nuclear era, people started reading about it in a PU textbook. So like that, quantum technology may come in some 10th PU, very basic level textbooks where its broad implications may be set already. That's
Yeah.
those things. And also some kind of outreach programs where different aspects, like what we said, quantum chemistry, finance, these things are highlighted, and such
That's right.
syllabi,
That's right.
such syllabi, and people getting together to teach it.
Yeah.
So that is important.
So I think the National Quantum Mission will promote some of this. There is an application type proposal that has not yet been shortlisted. Right now, the shortlists are only around hardware. The software layers will come in. Obviously, we need a lot of people who are looking at the applications, because what will you do if somebody builds a quantum computer? You cannot start thinking about it then, right? Because the investments in building a quantum computer are fairly significant. So we will have applications teams that are looking at some of these things, and a lot of it comes with domain knowledge. I mean, the quantum computer scientists do not have the domain knowledge that is for the application layers, and the application layers have to come from other domains, and interdisciplinary sort of research is almost inevitable, right, for this to be a success.
Thank you.
Very much, sir. Thank you very much.
Do we have any questions from the participants? I'm not entirely sure if they can unmute themselves, but maybe they can use the chat box.
Yes, sir. Yes, sir. Any other questions from the participants?
Professor, thank you very much for a very lucid and scholarly talk on translating quantum technologies, National Quantum Mission. From basics, you explained so well. I'm sure students who have joined and also faculty really benefited by your talk. On behalf of KSTA and all the participants, I thank you immensely once again. Thank you, Professor.
Thank you very much. Thank you very much.
I also thank Dr. Usha Madam and Dr. Sudha Madam. They have been supporting us developing strategy paper. We will be requesting you also, Professor, for your kind, guidance and help in preparing strategy paper. I think Dr. Usha Madam will also concur with me.
Yeah,
Absolutely. I will confess, I'm seeing a couple of questions in the chat box on startups. What are the areas those quantum startups should focus on? It's a tough call right now because, as I said, it's early days. And right now, there is opportunities in doing a lot of classical things to enable the quantum mission. So you could be, I know startups are working on random number generators, but you have to be very careful because how many random number generators are you going to put in and where are you going to put in and what are you going to do with them? You have to answer those questions. So startups need to be a little careful about how they jump into this. They have to go through a proper discovery. They have to understand where the opportunities lie and who their customers are.
Correct.
Right. The customers today are primarily in the government sector, and that is not a very healthy situation. So we need to develop customers in the private sector. So I don't have a straight answer to what areas those startups should focus on, but I would say just be very careful, and that is true not just of quantum, it's of all startups, right? One has to do the customer discovery and understand who's going to pay for your technology before you start building it out. Right?
Yes.
Yeah. So regarding this training and so on, I think absolutely, definitely, we've been talking a lot. I was also talking to some faculty at RV College. There's a lot of interest, and getting together to do these strategy papers is important. I will confess that today my strategy papers are all written by AI. So right, it does a very good job.
In any case, Karnataka should also get a kind of their interest put together, and we try to have something. So we welcome you to.
Sure, happy to help. Happy to help.
Please,
all right.
Please.
Okay.
Thank you.
Thank you very much. Thank you.
Thank you very much, Professor. Madam, Usha Madam, thank you very much. Thank you very much.
Namaskara. Thank you.
Dr. Sudha Madam, thank you. We have senior faculties who have joined, Dr. Girija, Dr. Pradeep, Dr. Abhishek, Dr. Girish, Dr. Moisina, Dr. Raj Kulkarni, Dr. Zina, Dr. Santosh. Thank you very much. Dr. Akshata is with us. He is one of the expert committee members of STA Group on Strategy Paper Development. Thank you for all of you. And we'll be joining tomorrow for another talk by Dr. Anil at 3:30. Please all of you join. Thank you very much.